Hello, welcome back again. We are, in this week's topic, continuing the regression idea. So just to recap where we left off at the last period, we compared an independent variable, like say the income of a community, against a dependent variable, the poverty rate in that community, and was measuring if the income increases, what happens to the poverty rate. There is a lot more that regression can do. The first thing that we can build upon for extending regression is to allow multiple independent variables. It still is within the purview of linear regression here, but I'll change that to multivariate regression. And we're now switching from a single variable to many independent variables. So now instead of just looking at the effect of income upon the poverty rate, we can have several changes and several factors. So we might say, okay, we're going to still try to predict the poverty rate. After all, as we saw, regression is in its way a form of prediction. But now to say the poverty rate, we're predicting it from the income, but also the proportion over 65, the average family size, and perhaps a measure of income inequality. So now we might say a frequently used index for measuring inequality is called the Gini Index. In the sense it's not particularly relevant here what measure you use. We can say we might expect as income goes up, poverty rate should go down. As the percent over 65 goes up, thanks to Medicare and Social Security, where most senior citizens, most over 65, have a guaranteed minimum income, we may expect the poverty rate also to decrease. The family size, a larger family would need a larger income to get above the poverty threshold. So we might expect a positive relationship there. Likewise, if there is more inequality in a community, then there we would expect more people well off, but also more under the poverty line. So now we have 4 different independent variables. Behind the scenes, the mathematics is pretty similar. It becomes more complex because we have, instead of if you remember, we had geometrically y equals mx plus b, or y equals an intercept plus a coefficient times our independent variable. What we're simply doing here is saying, okay, I now have 4 independent variables. I'm just going to add them in. And we still have our errors, our residuals, represented here by the Greek letter epsilon. So all we have done is add a few terms to this equation that really the software is estimating. In terms of how it goes, how it works, it's basically the same tool. All you do is, when instead of just sliding one variable over where it says independent variables or x variables, you slide over several. So the mechanics of running it in the software, pretty much the same. What's different is the interpretation. It becomes more complex. So we have the intercept still. If you recall, that's the value that had been, we called it the expected value of y, or the dependent variable, if the independent variable was 0. Now it's if every single independent variable is 0. The odds of every single independent variable being 0, I can already roll that out. 0 income, I don't think there would be a community where everybody has 0 income. So we can roll out the intercept from ever actually happening. Probably not a useful indicator here, but it's needed for the math. We would focus now on, instead of just the beta coefficient, we would now focus on 4 coefficients. So we have those 4, and each of those coefficients, so I'll put up here what we might see in a table. I'll just abbreviate some here. So percent 65 plus, family size, and inequality. We would still get, in our table, we would still have a coefficient. But now we have 4 of them. So the inequality, well, recognizing how we interpret the coefficients, it's what happens if the value of income goes up by $1, 1 unit. What happens to the poverty rate? That would be very little by itself. Let's just say you get 0.00036. So every dollar it goes down, but if you increase $1,000 for the income, the poverty rate drops by about 1/3%. Increase the average income by $10,000, it drops by 0.6%, this might be believable. And there is going to be a p-value or a probability associated with this. Income probably has a pretty low probability. The probability here, and this is where we're getting multiple p-values. Each of them has its own specific null hypothesis within this overarching method. This p-value is looking at the null hypothesis that this variable, income, has no effect on the dependent variable. So for this, we would say, for income, we'd say, yeah, there is an effect. Not a surprise. Percent over 65. The effect, overall effect may be bigger, but because this is a percent, poverty rate is the percent under the poverty line, increase the percent over 65 by 1, the poverty rate drops by 0.43%. Unlike here, we cannot increase the percent over 65 by 10,000 units. That's obviously very silly. We can't have 10,000%. So it's important to recognize these coefficients are in the units of that variable that can change from one variable to another. And the p-value, that may show up probably as a significant relationship. Maybe yes, maybe no in the real data. But for the numbers I'm writing here, for the sake of argument, we'll say it is. Family size, we had said, okay, as family size increases, that may lead to an increase in the poverty rate, because a larger family size, you need a larger income. Maybe, however, yes, the increase in the family size by one person, so now instead of 0 to 100, the unit here is the number of people. 1 to a really large family might have 8. So that can be a large coefficient and still not be significant. That ultimately would say, okay, there wasn't actually a relationship there between the family size and the poverty rate. Inequality, the Gini Index goes from 0 to 1, so this is going to end up being a pretty large coefficient. As it increases even by 0.1, we might have a couple percent rise in the poverty rate. And that too could be significant. We have these, and there is one last thing. Just as in the regular ordinary least squares, univariate or bivariate regression that we saw in the previous video, there's an R-squared that measured how strong the relationship is. We have R-squared again in a multivariate setting. And that might be 0.63. What that is telling us is these 4 variables collectively explain 63% of the variation in the poverty rate. So that's telling us, in a sense, how good our predictions are. And we can then again get a p-value. In this case, with 3 significant variables, it's going to be very, very low. That if you have significant variables for their coefficients having an effect, this is the p-value here. Looking at R-squared, the null hypothesis is that collectively they don't explain much of the variation, or any. Well, if 3 of the 4 individually do, the overall pretty much has to. There is one other value you might see in a multivariate setting. Something called an adjusted R-squared. The reason we have an adjusted R-squared is, if you think about what I just said in terms of what R-squared means in a multivariate setting, how much of the overall variation in the dependent variable, poverty rate, how much of that can be explained by the set of independent variables you are doing and using? You could give yourself a really high, a really great R-squared value just by throwing everything in the kitchen sink into the regression model and have 15, 20, 30, 40, however many variables you want as independent variables. Every additional one cannot make your prediction worse. If it has no relationship, its coefficient is going to be 0, and it will just be ignored. It hasn't made the regression any worse by including it. It might make it better. It could do nothing. However, when we go through and we say, okay, I now created a regression model with 30 independent variables, and you get a table with 30 coefficients, 30 p-values, it becomes very challenging to distill a message. It's not that useful. And so what is done is an adjustment to the R-squared value is made by penalizing having additional variables, additional independent variables. That way, you can go through, and when you pick the model with the best adjusted R-squared, you can be certain you don't have too many variables. Each of those variables is contributing in some way to the overall model. And so in this case, I might opt to try again. Family size is not significant. I'll remove it. What this would do, it would decrease the R-squared. It might go from 0.63 to 0.62. It wasn't contributing much. That R-squared is going to go down. The p-value is going to go slightly up. But the adjusted R-squared might increase because whatever gains I got by having that variable on family size and the R-squared, 0.01, is offset by the penalty of the adjustment for having an extra variable. And so we might want to identify our best model by having adjusted R-squared and saying what is the best, highest adjusted R-squared. At what point does adding variables create more penalty than it actually gives an explanation. And that's when we stop adding variables. So that's the information we'll get in this table. And there is one more interpretation issue to note within a multivariate setting, which is exactly what these coefficients mean. If I do a single bivariate regression of just income against the poverty rate, the coefficient will not be the same. It will not be the same because I have these other variables. And so if we look here at the math here, and I think about what goes into this coefficient, saying if I increase x1 by 1 unit, what happens to beta 1? That is also assuming these other values stay exactly the same. That is maybe not, that's probably not guaranteed in practice, that income and age would be related to each other, probably. Those on a Social Security fixed income probably have a lower than average income. So to say these are truly, completely independent and unrelated to each other is a bit of a stretch. We do hope, though, that they are not too closely related to each other either. So what this coefficient is saying is kind of a hypothetical situation of, I have two counties, two communities. They have the same percent over 65. Both at 21.3% of the population at 65 years or older. They have the exact same Gini Inequality Index at 0.73. Keeping those two variables the same, and I increase the income by $1. What happens to the poverty rate in that assumption of everything was staying the same? The term for that comes up is the marginal effect. Recognizing if I increase this, I may decrease that, or vice versa. That said, above the effect of income, above and beyond any effect of age or inequality, is what you see here. So, okay, we go through this process. We have our multivariate regression. If you have questions, again, I hope you send me emails or use the discussion boards. You may have noticed that, as with the t-test, as with ANOVA, spatial issues or geography is distinctly lacking from this board. There then could be an additional question of, well, I have an R-squared of 0.62. The poverty rate, there's other stuff going on that affects the poverty rate. We may then want to ask, is there a spatial pattern to the prediction, and especially, is there a spatial pattern to those errors, to the residuals? If so, we might come to the conclusion, my model needs an additional geographic or spatial component. So I might then go and take that residual, using a different way of getting to the regression in Geoda, we can actually add the residuals to the table itself as a new variable. Once we have that, as a new variable, do Moran's eye, do at least a spatial autocorrelation analysis, not of the independent variables, not of the dependent variables, but of the residuals. And we see, is there a spatial pattern to the errors that I make? So I might say, okay, I'm looking at the poverty rate, and I have income, I have the age structure, the percent over 65, I have the family size, I have the inequality. That might explain the poverty rate better in, say, the northern half of West Virginia, but not in the southern half. And so I have a larger error in the southern part of the state. Or I find a spatial pattern in that those variables are over-predicting, saying there's too much poverty in the north, so the north has less poverty than we were expecting, but the south has more poverty than we were expecting. So we could see Lisa clusters, high-high or low-low, of the errors, of the residuals. The main thing here, this in many situations doesn't directly give a lot of useful information. Sometimes the clusters could. That might give you insight into, okay, something is missing. What else could be causing an excess of poverty in the southern part of the state? So that might kind of get the brain going, brainstorming of different changes to the model that we can make, to the regression analysis. It could, additionally, especially if I find Moran's eye is significant, if I find a strong signal for there being autocorrelation of the residuals, that may suggest doing one of several forms of spatial regression. So, if I find significant Moran's eye, I might say, okay, something else is going on. The question then becomes, what is going on? How I answer that question. What do I think is causing a spatial pattern of the errors? Can decide which form of spatial regression to use. Here I will discuss three. Two of them are in the lab. The third is in ArcGIS, but not in Geoda. So once we all have reliable use of Arc again, it could be good to know what that is, but it's not going to be in the lab. Meanwhile, the two that are in the lab, incidentally, are not in ArcGIS. So I guess it's a good complementarity between the two software systems. So the first, and perhaps the most straightforward, is if there is just some missing factor, some other geographic or spatial process that I don't think I've accounted for or included, even if I don't necessarily know what that is, or I have a good hypothesis of what it is, but I don't have the data for it, I can use something called a spatial error regression. So I will illustrate them by extending, in a sense, this formula. Well, even though we will be doing it in a multivariate setting, the ideas are the same basically. Just for simplicity's sake, I will do them in the bivariate for this. What the spatial error does is it takes this error, or residual term, and splits it in half into two components. And just bringing up because they use different Greek letters. And what I've done here, I'll add another color here. So what it's doing is to say the neighbor's average error. So I have consistently over-predicted the value in the area around Mon County. Okay, I'm going to then say that over-prediction comes into here. The weights matrix, this is the spatial weights that we have seen in spatial autocorrelation. Do they share a border? Are they within a certain distance? Are they the 5 nearest neighbors? What have you. However you are defining neighbors, it shows up again. That's why this idea of the neighborhood really is a fairly important geographic concept for spatial analysis. In this box is the average error of the neighbor. So the spatial error, which is basically the different errors of the neighbors, times the weights matrix. So it comes up with a average of the neighbor's errors times some coefficient. It's like a beta coefficient, it's just given a different Greek letter. Lambda in Geographic. Other sources may use different letters. And we then still have a residual. This isn't going to fix all of the errors, so we still have that residual term as before. Now, if this lambda is significant, as with other coefficients, we will get that lambda value, we will get a p-value for it. The lambda value itself is kind of hard to interpret, probably. But if it is significant, then we can say, yeah, there is some extra spatial process that is affecting the poverty rate, or whatever our dependent variable is. This is spatial error. Spatial lag, as we'll see, will look very similar. Not the same, but really quite similar. The rationale is the term that is often used is spillover of the dependent variable. So to say, in a sense, it's the opposite of what happens in Vegas stays in Vegas. If I increase the poverty rate of Mon County, does that increase by itself increase the poverty rate of my neighbors? So if Mon County becomes more impoverished, I can guarantee Preston County also becomes more impoverished. Or, if I increase Preston County, Mon County becomes more impoverished. So is there some kind of relationship within the dependent variable that a change in the value, whether positive, whether negative, spills over into neighboring counties? If I can answer this as a yes, then I would want spatial lag regression. And instead of saying the neighbor's average error because of some missing spatial process, now it's the neighbor's average dependent value. That is basically treated as another it's usually done with a Greek letter that I like to call squiggle. But now instead of taking the error and splitting it, I am taking the neighbor's dependent variable. So the neighbor's average y value, or dependent variable, and treating this as its own independent variable, I get this lag coefficient, and to say, well, is this a significant factor in impacting my dependent variable? So again, does the neighbor's average poverty rate, Preston, Taylor, Harrison, or Marion, Wetzel, do those counties impact the poverty rate of Mon County, whether positive or negative? If I increase that average by 1 unit, okay, what happens to the coefficient? In practice, chances are if the spatial lag coefficient is significant, the spatial error usually would be as well. But they are, as you can see here, whether it's spillover of the dependent variable or just some missing spatial process, their interpretations are different even if the answers are often similar. These two are in Geoda. In ArcGIS, we have a third version of spatial regression. As I said, it's not going to be on the lab because we aren't guaranteed access to Arc. In a way, if we think of the question about the relationship, I might say, oh, and we've kind of hinted at this with what I did with the mining versus non-mining areas in regression in the first lab, or regression lab, is to say, does the relationship between income and poverty itself vary across the study area? So is the relationship between income and poverty the same in the northern part of the state versus the southern part of the state? In regular regression, in spatial error, in spatial lag, it is assuming those relationships are constant everywhere in the state. Geographically weighted regression does not make that assumption. If we look over here, we can essentially say spatial error builds geography or the spatial weights matrix in here. Spatial lag puts it in the Y category. Even though it shows up here, it's using Y. Variation in, really it's variation in the beta coefficient over space is the third element, which is geographically weighted regression. Of course, the blue marker had to fall. What this does, and what mathematically what's going on here is not obvious. It's no longer truly doing a complete statewide regression. It is instead doing, if you're working at West Virginia, 55 separate regressions. One for every county. Each regression only uses the neighborhood around that county. If you think about this, you might then be recognizing, now instead of, this has added one extra coefficient. This adds one extra coefficient. This says, now instead of one coefficient for each independent variable, I have 55. One value for every county. If we have a value for every observation, it makes sense. The results here, they're not as a table anymore, they are as a map. And you map out the change of the coefficient from one place to another. the change of the intercept even from one place to another. And the error can be mapped as well. And so interpretation, we map the p-value as it goes all the way across the study area. One thing that is useful here that doesn't show up typically in the other two. If we have a variable, a relationship, independent variable versus dependent, that statewide doesn't show up as significant. Geographically weighted regression may reveal that we're kind of looking at the wrong scale. If a variable is strongly significant in the positive direction in the northern part of the state, equally significant but in the inverse or negative direction in the southern part of the state, if we only look statewide, they will cancel each other out. I will show up as not significant at all, anywhere, because we're assuming it's a constant value across the entire state. For GWR, we can say, actually, in different parts of the state, it's a different relationship. There's a much more complex and more interesting pattern going on here that we just never saw. So those are the three forms of spatial regression that we are most common in geography. There are indeed other forms beyond just these three. They would be, to borrow a phrase, beyond the scope of this course. So, just to wrap up regression, the null hypothesis for regression is that there's no relationship. Whether that is at the level of each individual coefficient, no relationship between that individual independent variable and the dependent variable, or of the overall R-squared, no collective relationship with the dependent variable. We can look at correlation, how closely related are they? That can be positive or direct, where as one goes up, the other goes up. Or that can be inverse or negative, as one goes up, the other goes down. The most common and simplest form is a linear regression form. And there can be a few different interpretation concerns. I'll bring up a couple. One of them is, and especially shows up with geographically weighted regression in a multivariate setting, to have a reliable estimate, you need to have plenty of observations for every single independent variable. If we think of a scatter plot, if I have 2 points, I can draw a line through it perfectly. For the math to work, I only need 2 points for a single line. It basically means for every, in a multivariate setting, if I have n independent variables, I really only need n plus 1 observations for the math to work, but it's not reliable. Usually we like to have 5 or 10 observations for every single independent variable. If we go up to, say, geographically weighted regression, our neighborhood sets that number of observations. So how big is the neighborhood, not how big is the study area. In practice, that means with West Virginia, 55 counties, stopping at 5 or 6 variables is usually not too bad as just a way of thinking, as a heuristic. The other is in interpreting the coefficients. If I think about a scatter plot, and I have my coefficient representing the slope here, geometrically, we can extend that as far as I want. But that might be a risky thing to do. We only have data in this range, so really that's all we can speak to, that's all we know about. Sometimes we just end up in silly territory. If I end up saying, I'm going to predict a negative poverty rate, well, I'm pretty sure I can conclude a poverty rate of -3% is going to be wrong. So there's that caution. But it also means as income increases, there may just simply be a base level of poverty that's always present. If I don't get to there, that part is missing from my data. And so extending the regression line, the coefficient, beyond what data I have, it can lead to interpretation problems. Without getting more data, you can't solve that. But that said, regression is a very powerful, as I said, opened up, it's the workhorse of statistics. It is the most commonly used technique in geography, probably in statistics as a whole. So it's very useful, very powerful in what it can tell us about the relationships between different variables. There are many versions and extensions to regression that I haven't covered. If you have questions, feel free to ask. So with that, have a great whatever time of day you are watching this. And I hope this has been useful for you and informative for completing this topic's lab. Keep staying safe, keep staying healthy. Goodbye.